Right. We've talked about rotation of the atmosphere. We've talked about putting moisture into the atmosphere through various mechanisms. We know that water contains lots of latent heat. Latent heat is energy. So the more moisture we have in the atmosphere, particularly as cloud mass, the larger the precipitation events are going to be. As well, the larger the mass of atmospheric lifting, the larger the low pressure cell is going to be, and the bigger the difference between high and low pressure cells there are, which is going to then influence the wind conditions. They're going to be stronger wind conditions. So these all play into atmospheric disturbance, better known as storm cells. So we're going to generate some storms for you. Before we generate and talk about storms, we need to talk a little bit about air masses, and we talked a little bit about air masses already without calling them air masses. What we said a little while ago when we were talking about humidity is that the humidity is higher over bodies of water, which means that that water is going to evaporate and it's going to infuse the air above it with some moisture and pass along energy. Land masses, on the other hand, have very little opportunity to put moisture in the atmosphere, so we're going to have dry air masses. So we've talked about those two conditions. So the larger a land mass, the larger a water body, the larger the air mass above those are going to be. So we're going to generate these very large air masses that encompass across a continent for the most part, and that can be 10 miles deep or so. For the most part, these air masses at maturity, when they're oldest, are going to be homogeneous. There's going to be statistically little difference in temperature and in moisture regime across that air mass, except for when you get to the edges, when those air masses meet an adjacent air mass. And then there's going to be variability at the edges. And that's where you're going to have atmospheric disturbance for the most part. Not there's going to be other atmospheric disturbances that we're going to talk about, but it's at the edges where variability takes place. So the longer that these air masses are in situ, are in place, the more stable they're going to be. Now, spring and fall are the seasons when the sun is moving across latitudes. They're pulling air masses along with them, or they're pushing air masses, depending on the direction that that sun is moving in. And so because those air masses are moving now, they become unstable, and they're growing or they're shrinking. So by the time we've moved through spring, we have eroded the winter air masses, and we're growing the summer air masses. So from June through August, September, the air masses for the summer are getting larger and larger and larger and more stable for the northern hemisphere. The same can be said in the southern hemisphere winter conditions. Those winter air masses are getting larger and larger and larger. The reverse is true as we move from September through December, that the air masses become smaller, the summer air masses become smaller, and the winter air masses become larger. So through December, January, February, and we're in February now, the air mass has been in place for quite a long time. Is a little more stable because it's larger, those winter air masses. All right. We've got some nomenclature that we can address, and because temperature and moisture together make up the characteristics of an air mass, we need to define them as such. So a dry air mass is continental, like the ones that generated over a body of land. Maritime air masses are moist, they're wet, they have a lot of energy in them. And they generated over a large body of water. Think oceans as opposed to larger seas or freshwater bodies like the Great Lakes. Temperature, on the other hand, has more variability. If we go from the poles, where there is some change in linguistics because changing conditions, the North Pole and the South Pole have slightly different conditions, so they have slightly different names. In the Northern Hemisphere, it's a polar land mass or air mass. In the Southern Hemisphere, it's the Antarctic air mass, and that's because in the northern hemisphere there is more water, and water is going to have more heat radiated from it, so the polar air above it is going to be a little warmer than the Antarctic air mass, because you know by now that land mass can't hold a lot of energy, doesn't radiate a lot of energy, so the Antarctic air mass is going to be colder. So back to the northern hemisphere, we move southward. We then get an Arctic air mass. The air is warming up. Think Canada, think the northern states, think northern Europe across to northern Asia. Think middle states, southern states now. In terms of latitude, we've got tropical air masses that then penetrate through to Mexico and Central America. Think through the Mediterranean nations, through North Africa for that tropical air mass. Equatorial is going to be in and around the intertropical convergence zone that we've talked about a couple of times now. Then the mirror image is true for the southern hemisphere. So we go from equatorial to tropical at the same latitudes we see them in the northern hemisphere. We get an Arctic at the same latitude that we have in the northern hemisphere, but then we have the Antarctic. All right. Graphically then, we can look at a summer pattern here for the northern hemisphere in North America. What we get is this air mass right in the middle here that I want to draw your attention to. It's a continental tropical air mass, only exists in the summertime. All right, we do not get a winter equivalent here. That's because this is large enough of an area to generate significant amount of dry heat. So we get a continental tropical over northern Mexico, Texas, Arizona, parts of Oklahoma generate this air mass. At these similar latitudes across these warm bodies of water, we get a maritime tropical air mass, and I want to draw your attention to these arrows. This air mass is sitting a little further north. The Coriolis effect is going to push this air inland, and it's moisture laden, so the center part of North America, we're going to see some moisture infusion in these central states here. So Missouri, Kansas is going to get some well-needed moisture from this air mass. That Coriolis effect for this air mass on this side is going to push up the east side of the Appalachians, infusing moisture all the way up through to Newfoundland as a result. Coriolis, rotates these air masses which are buoyant clockwise, so we're going to rotate and bring moisture and warm temperature into the Baja, into the Sea of Cortez, also known as the Gulf of Mexico or Gulf of California, and then into northern Texas, and then across into Oregon, maybe a little bit into southern Washington state. The polar maritime air mass sits above it. It starts to appear and sits in summer position across from Washington state and Oregon. Its equivalent sits out here at roughly the same latitude, and these are also influenced by the Coriolis, so this air mass is going to rotate, penetrate inland, across Alaska, into the Yukon, into British Columbia, and note the arrow here into Washington state. We can't see it on this side, but the same influence rotation is coming across Iceland, across the Nordic states, across Great Britain. Continental polar, dry continental air that is cooler is penetrated across most of Canada here. Note the arrows, a little bit harder to see because of the way these were graphed out, but you can see that we're getting penetration southward with this air mass. It's just tipping into the northern parts of the states. And then we see the genesis of this continental polar air mass up here as well, right? It's a little like an Arctic air mass. Okay, change that to a winter pattern. we see the loss of this continental tropical. The maritime tropical has moved further south on both sides. We see that the rotation isn't penetrating as far inland for both of these warm air masses, more moist air masses, but our maritime polar has now sunk further south. Remember this, the sun is in the southern hemisphere, so just like a slinky, we're pulling everything southward. So we're dipping into Northern California with this maritime polar. Same thing with this air mass over here. It's dipping further into Europe as well. But this continental polar air mass is now penetrating further into the United States. It's sitting roughly at the same latitude, but its influence is further. Think of the polar vortexes that we have been talking about over the last several years. We talk about them like they're a new thing, but these polar vortexes are not new names. The media has now picked them up. And so polar vortexes are going to bring this air mass further south. And then we've got this continental Arctic air mass now that has generated over the winter months, sitting right up here in these northern Canadian islands. Put these two graphics side by side just for comparison, and you can see how much these air masses have moved north and south over a 6-month period of time, really changing the amount of temperature across these landscapes and the amount of moisture that these landscapes receive. Again, spring and fall is when these air masses are moving, and as they're moving, they're changing the amount of moisture that you get. It's these edges that you're going to get instability at for the most part. So as we're moving into spring over the next several weeks, what's going to happen is this continental polar air mass is going to be retracting, and the maritime tropical air mass is going to be expanding, and these two edges are going to come in contact with each other, and as they're moving northward, that's where we're going to get this oscillation of springtime precipitation events. They're first going to start as wet snowfalls and then dry cooler periods, followed by another snowfall event. That's usually the pattern in March. As we move into April, then we move from snow to rain, and then we get rainfall events and then dry events and then rainfall events. So you'll see this oscillating pattern of wet, dry through to the start of summer. And then summer, generally we're going to have afternoon rainfalls, but we're not going to have day-long rainfall events.